So here's a video that's going to look at moving air through an air handler. This is similar to a couple questions on your test that I noticed people got wrong, where you're having to figure out how much heating or cooling a heating coil or a cooling coil in the central air handler has to do to make the desired supply air temperature. So in this scenario, we're ignoring fan heat, so there's no fan heat going on. It's a 10,000 CFM air handler with 35% minimum outside air. The supply air temperature, the desired supply air temperature is 55 degrees. Your chilled water is being provided by a chiller that has efficiency of 1 kW per ton. Your boiler is providing heat at an efficiency of 80% AFUE, and you've got 10 hours of runtime. So in this first scenario, we've got an outside air percentage of 30 degrees, and we've got a return air temperature of 72 degrees. So the first thing that we want to do is figure out, can we make 55 degrees of supply air temperature without violating our 35% minimum outside air? So we do our percentage outside air equation, which looks at mixed air temperature, 55, because that's the same as our desired supply air temperature, so we won't have to do any heating or cooling under this scenario, minus return air temperature, over outside air temperature minus return air temperature. And so we get this equals negative 17 over negative 42, which equals 40.5%. So in this scenario, we are greater than our minimum outside air at 35%, and we're able to make our discharge air temperature without adding any heating or cooling. So in this scenario, if I was to ask you how much heating or cooling is being added, the answer is 0. So now we're going to change things up a little bit to figure out what it would be like if we had to add heating or cooling. So let's change our outside air temperature to 10 degrees. This should probably require us to add some heating into the equation. And so again, we do the same equation and say 55 minus 72, so mixed air temperature minus return air temperature, over outside air temperature minus return air temperature, which equals negative 17 over negative 62, which equals 27%. Now we can't do that because we need to have at least minimum outside air of 35%. So we need to figure out what is our temperature at the mixed air temperature going to be. So we can say 0.35 times 10 plus 0.65 times 72. So 35% at 10 degrees, 65% at 72 degrees, and that gives us 50.3 degrees. So if we're at minimum outside air, our mixed air temperature is going to be 50.3 degrees, which is not enough. We need to heat it up. So this temperature after the heating coil right here is going to be adding some heat through this heating coil. And so now we have to figure out how much heat. So we use our air side equation, 1.08 times CFM, which is 10,000, times delta T, which is the difference between our desired supply air temperature and our mixed air temperature, which is 4.7 degrees. That is going to give us a BTUH of 50,760 BTU per hour. So this is a this is a unit of power, not energy. And so what we have to do is we have to add the element of time, and we have to add the element of the efficiency into it. And so what we have here is we've got 50,760 BTUH times 10 hours. So the hours are going to cancel out, so now we're left with BTUs, and we're going to divide it by 0.80 efficiency, which gives us 634,500 BTUs, and we divide that by 100,000, which is the conversion between BTUs and therms. And so we get 6.34 therms that happen over the course of this 10-hour period to add 4.7 degrees and get to our desired supply air temperature from our mixed air temperature that had to rely on the minimum outside air. So in the first scenario, we didn't have to add any heating or cooling. This one, we're adding some heating, but keep in mind what I saw a lot of you do was they had an answer that had both heating and cooling being added in this scenario. So now there was cooling being added by the cooling coil in this scenario. You should never have a heating coil and a cooling coil adding energy to the airstream at the same time. It's one or the other. And if you're ever going out to a building where you see that happening, it's called simultaneous heating and cooling, and it's a problem that needs to get fixed. So if we're adding heat, we're not adding cooling. So if the next question says how much cooling is required, the answer is 0. So let's do one more scenario looking at the cooling side. And so again, what we're going to do is we're going to say now that our outside air temperature is not 10, it is, we'll say, 90. So right now, you don't even have to go through the process of figuring out if you're going to violate minimum outside air, because you for sure are. 90 is greater than 55, and 72 is greater than 55. So no combination of those two numbers would ever equal 55. So we can jump right to the part to figuring out how much, what our mixed air temperature is going to be. So we've got 0.35, 35% minimum outside air, times 90, plus 0.65 times 72, and that equals 78.3 degrees Fahrenheit. And so again, we're going to need to cool that down to 55, and so we subtract 55 from that, and we get 23.3. So same equation here, 1.08 times CFM times the delta T, which is 78.3 minus 55. So we've got 23.3. And that is going to give us 251,640 BTU-H. So we take that number, so we got 251,640 times 10 hours gives us 2.516 400,000 BTUs. Okay, so now that we have that number, we need to convert that number to figure out how much cooling is being done. So there's no heating that's going to be done. Now we're looking at cooling. So we want to take this number and turn it into tons, because we know it's 1 kW per ton. So if we can turn this into ton hours, we can figure out how many kilowatt hours. So we're going to divide this by 12,000, which is the conversion between BTUs to ton hours, and that comes up with 209.7 ton hours. And we know that our efficiency is 1 kW per ton, so we just have to multiply by 1 to get us 209.7 kilowatt hours of energy is what it takes over the course of 10 hours to change the mixed air temperature from 78.3 to 55.